we were using the inverting amplifier for both the integrator and differentiator, right? So what is the inverting amplifier gain? We had the inverting amplifier plus minus for the general case where we have impedances. Impedance VI, this is Z2, Z1. What is the V output over V input is equal to negative Z2 over Z1 of S. That was where we started on both cases, right? It's just one of them happened to have Z2 for the integrator. For the integrator, we happen to do what? We happen to have a resistor here, and then a capacitor in the feedback, right? For the differentiator, we happen to have the capacitor here and the resistor in the feedback, right? So both cases. So here, Z2 is 1 over SC. Here, Z1 is this R. Here, Z2 is R. Here, Z2 is 1 over SC. Right? So the derivations are exactly the same. But these are the derivations in the frequency domain, right? This gives us a transfer function, which is the frequency domain representation of the differentiator and integrator, right? If you apply something, an example we did a few classes ago where they gave us a sine wave with a certain peak value and a certain phase shift, you can take the sine wave with a certain value and phase shift and take it through this frequency domain plot that we can plot from. Again, remember these all reduced to a single time constant like transfer function. This reduced to a single time constant like transfer function. Meaning, if you look at here, this was the general case with the integrator, for example, with an R, was a single time constant transfer function, right? So we had DC gain, we had cutoff or break frequency. So if you had reduced it to whether it's a low pass or a high pass, so one of them was a low pass, I think the other one was a high pass. For the differentiator was a high pass. For this one was a integrator was a low pass filter. So assuming we're talking about the integrator, so we're talking about the low pass filter. If we have an input sine wave, and I want to see what the output is, I will go take my transfer function that I derived, right? And then I have a gain at every frequency, and I have a phase at every frequency. I will plot phase at every frequency as well, right? And then I can, and we did an example where we had the sine wave. But yesterday's example, we had a square wave, a pulse, right? This is not a sine wave. So I cannot just, I cannot just look at this frequency domain plot of magnitude and phase and say, and tell you what is the output. You have to derive the time domain representation or the time domain representation of the output. And that's what we spent time on yesterday. So we looked at the current flowing, we looked at the V output being the voltage across the capacitor. In this case, we had current flowing through here. So we found the relationship between current and voltage across a capacitor. IC equals C dVc by dt. So Vc is equal to 1 over C integral of I C dt. So we had to go to the time domain representation of the voltage across the capacitor to be able to calculate the output voltage. So we did that yesterday for both. The differentiator and integrator, and we looked at the non-ideal effects or the problems with the integrator. Sorry, go ahead, Ahmed.
Sorry, I want integrator or differentiator or the same.
No, this is an integrator, and this is a differentiator. Right? But they're both an inverting amplifier. They're both. You can start from here. You both start from here. It's just that one of them had Z2 equal 1 over SC. The other had Z2 equals R. One of them had Z1R, the other had Z2 1 over SC. Right? So, and then this is your transfer function, V output over V input. This is your time domain, this is your frequency domain transfer function. Right? And then from there you can draw your body plots, because you can reduce it to a single time constant representation, whether high pass or low pass. You can draw your break frequency, you can calculate where the gain becomes 0, and you can calculate your DC gain for both the differentiator and the integrator. What we found is that there was a non-ideal effect, right? What we found that was for the integrator there was a non-ideal effect when we looked at the transfer function. We found that the integrator was doing what? The DC gain of the integrator was becoming infinite at DC. So if I say if this is DC, right, then the gain here was infinite. Right? The DC gain of the integrator was infinite because the DC gain transfer function is integrator transfer function was 1 over s. Right? So if we derived it, we look at the derivation again, it was 1 over s. So it was infinite at DC. If s is 0, the gain is infinite. Right? So what did we do? We added a resistor in parallel. When we added this resistor in parallel, fine. Still, the output of the input is Z2 over Z1. What is Z2? Z2 is now this. Z1 is now this. So you can derive your transfer function in the frequency domain. And if I asked you to just merely put a sine wave through and draw the output of the sine wave, phase and magnitude, it's the same as the example we did before, some time back. Where we had a few sine waves with a few different frequencies and phase shifts and a few different magnitudes. No problem. But if I give you a waveform that is like a square wave, then it's where that's where the problem is. That's where you have to use your transient response work that we talked about from the end of 214, right? That's what we spent a lot of time on yesterday. Okay? And same thing with the differentiator. We found that the differentiator was acting like, or the transfer function of the differentiator was like this. Has no DC gain, but it has infinite high frequency gain. Infinite high frequency gain means what? Like if you have your input signal here, and your input is a square wave, this impulse rise or immediate rise contains huge, very large frequencies. The small magnitudes they may be, but it's large frequencies because it's something that's changing abruptly. Anything that changes abruptly, if you want to construct it using sine waves, you have to use many sine waves to keep adding the sine waves at the beginning of at the zero crossing, at the initial zero crossing. You keep adding more and more sine waves to be able to create this sudden rise, right? So that means it has very high frequency content. What is this circuit going to do to high frequency content? Amplify it significantly, right? So do we want to do that? That means if you're trying to, put a signal through a differentiator like this, and you want to differentiate something like, for example, a signal that looks like this, something that has some sudden rises. What is this amplifier going to do? Anytime it sees high frequencies, the gain will be infinite, right? So you will have these spikes in the output, huge spikes in the output because the gain is infinite at that point, right? So how did we solve this? We said that the solution to this, put a resistor in series. How can you derive the new transfer function? Again, Z2 over Z1, right? And then it's a single time constant. Same single time constant, just the configuration is different, right? And then what did this do to the frequency domain plot or the transfer function magnitude plot? It changed it to something like this. What did this resistor do to this frequency domain magnitude plot? It changed it to something like this, right? So why is this interesting? It's interesting because at low frequencies, I know what the gain is going to be. And this is interesting because at high frequencies, I know what the gain is going to be. Right? I will not have very high spike. If I have transitions in my input that contain high frequencies, they will be amplified to a certain level at the output, but they will not just be appearing as spikes. I know what they're going to be. I know what the magnitude will be. Okay? So that was the objective of yesterday's class. So we can move on. Okay, if we move on, we did this example, we did the differentiator. Okay, now we talk about some non-ideal effects. So the only non-ideal effect we talked about before was what? A DC gain instead of being infinite, we limited it to a certain value A, and you did this homework take home take home quiz where we derived it for the non-inverting, I think, and you derived it for the inverting, or vice versa, right? So one of them was not derived in text, and you derived it. So something else will pop up. So it's not just the fact that so the gain will not just be limited. The gain of an op-amp will also be frequency dependent, right? So we will talk about that in one of these sections here. Another imperfection is that, remember when we talked about common mode voltage and how we spent so much time trying to eliminate common mode voltage, right? And it was what? It was a DC voltage that was applied to both inputs at the same time, or a DC voltage applied to one of the terminals, and we had no way to pass it through, and we had no way but to allow it to pass through with a gain in an inverting and non-inverting configuration, right? So we happen to have an offset voltage, a DC offset voltage, due to the construction of the op-amp internally, inherently there. So even though if you take your two terminals of the op-amp and short them, create a short circuit. Just create a short circuit across the two terminals, meaning V2 minus V1 is theoretically 0. Your output will still saturate, right? So the output will still saturate. Why? Because there is a offset voltage internally, and and you can model it like this. So this section talks about this offset voltage. So even though I short my two terminals here, this is now my ideal op-amp. So this is more of a real op-amp, right? The real op-amp will have an offset voltage. If this offset voltage is present and you short the terminals, your output will still saturate, because the difference between the ideal op-amp's terminals exists. There's a DC value there, right?
What does the offset voltage do?
It's like it's a voltage that is added to your non-inverting terminal voltage. So if you have V2 a voltage here, you have it. For example, you have non-inverting amplifier. Non-inverting amplifier, you put your signal here, right? You put your signal here. You're putting your signal here, VI. This is ground. And then you have what? You have a resistor here to ground, and then you have your feedback. Right? If your signal input, if your signal is 0, so I'm bypassing this, I have feedback, which means that the difference between these two is 0, which means that the voltage here is 0, so there's no current going to flow here. So I have 0 at the input of the amplifier, theoretically speaking. If you do that, what do you expect at the output? Theoretically 0. But you're not. You're not going to get theoretically 0, because the non-inverting terminal actually has a DC voltage here with respect to ground. Right? So the output will include the offset voltage, and it's also going to be amplified. Right? Because it's a DC voltage with respect to ground. It's like, okay, bring this back instead of this one. So the output here will actually be amplified. So you will see V offset amplified by the non-inverting gain, which is non-inverting amplifier gain, which is 1 plus R2 over R1. Right? So it's a really bad thing. Right? So that's one of the non-ideal effects we're going to look at. We're also going to look at the effect of having current actually flowing into the terminals of the op-amp. So these are called bias currents. Bias currents are currents that are not due to your input impedance. Right? They are actually due to the fact that you have circuits inside here that require certain operating points to be operated at a certain operating point, meaning there will be certain currents flowing and voltages across the transistors that are making up this circuit that are going to force small values of current to go through the op-amp. This has nothing to do with your input impedance, has nothing to do with your circuit that you created around it. Right? They're there because of the device. Right? And we will see what the effect of those are. Ideally, we would like, of course, to minimize the effect of these as much as possible, right? So if we find a way to not amplify the offset voltage and have the offset voltage go through, fine. If it's a few millivolts and my supply rails are plus minus 13 volts, fine. 2-3 millivolts, and the output may not be too much harm, right? I may have to figure out a way. Maybe I remove the average from the output if I want, or I do something in the output to.
Take this to
Yeah. In all real op amps, will have offset voltages. They will have bias currents. So actually, I have a data sheet for an op amp. So this is a real op amp. I think you're using that in the lab, the 741. Have you used that in the lab or not yet?
No.
Not yet?
No,
You did, right?
741.
Yeah, the 741 op amp, right? So this is a Texas Instruments op amp. It's a device from Texas Instruments. This is the data sheet. If you search online, you'll find it. You find it has a lot of stuff. At the beginning, the more interesting stuff are the electrical specs. Okay, so input offset voltage. So it's in the range of 1 to 5 millivolts, and then it seems to, I guess, be effective. This is at 25 degrees C. I guess it's at certain other temperatures it can go up to 6 millivolts.
What does that mean, 25, like the temperature? Does that mean
The
like
test was done at 25 degrees Celsius.
Okay.
The manufacturer guarantees that the device will behave within this spec at 25 degrees Celsius.
Do they tell you like the degree that it just doesn't behave?
They tell you. 1 second. I think. Of course, there's a temperature range. So there's a input blah blah blah. Slew rate, electrical current. I think maybe in the thermal. So they tell you that the junction to ambient. No, not this one. Temperature. So they guarantee the operation of this device from minus 55 degrees Celsius to 125 degrees Celsius, or for certain versions of it, only from 0 to 70 degrees Celsius. So obviously this one is cheaper. This is a 741, and this is also a 741. But the manufacturing process may be different between this device, the 741A and 741, versus the C. Right? This is a military grade probably device, military or automotive rated, right? So, because military or automotive devices typically operate with wider temperature ranges, so you can buy these devices, and they will be screened, or the manufacturing process may be different, and they would also tell you that, for example, they would tell you, here this is microvolt per degree C. So the average input offset voltage drift. So the offset, this value of offset voltage will drift with temperature. It's not a constant value. And here they're telling you that the drift is about 15 microvolts per degree Celsius. So anytime you change the temperature by 1 degree, expect 50 microvolt change in the plus or minus direction. Okay, this is very random, right? It's depending on the manufacturing process. You cannot tell. You have to design within that range. So when you design your circuit, you make sure that you account for the full range in plus minus. Yeah. These are the bias currents, input bias currents that we're going to talk about. 30 to 80 nanoamps for this specific device. So these currents that will be going into the pins of the op amp will be 30 to 80 nanoamps. They will also be affected by temperature. So they will tell you. We'll go back to the data sheet after we talk about a few things. So each one we're going to go back to the data sheet and show you that it exists here. So, okay, so how do we deal with this offset voltage, or how do you, first, to deal with it, you have to measure it, right? So to measure it, one good way to measure it is to do what I just described before. Build it as build an amplifier around it, but make your input voltage 0. Right, so and let's see what happens. I think that's what they do. Actually, before doing that, so if I have an amplifier in open loop, right, and there is no offset voltage, right, how do I draw the relationship between input and output? This is VID, the differential input of the amplifier. If VID has any value, what's going to happen for the ideal op amp? VID is the voltage between these two terminals. What's going to happen if I have voltage between these two terminals? The output will saturate, right? So it's V2 minus V1 multiplied by the gain is going to be V output. This is VID over times V output, right?
So V2 doesn't equal to V1, then it's going to saturate.
Yeah. And that's why if the offset voltage exists and you put a short circuit, I mean, here, if you have offset voltage, you put a short circuit here, but you have an offset voltage. So what's going to happen to the op amp output? It will saturate. This is V offset. It will saturate, but you cannot measure it. You don't know what the offset is, right? Because it's finished. The op-amp will saturate. There's no way to measure it here. For you to measure it and know what your offset is, you have to construct some circuit around it that you control the gain for. So you can, okay, now my gain is X. If I take the output now and divide it by X, then I know what my offset voltage is. I can deal with it in that case, yeah. So anyway, so if the circuit is ideal and there's no offset voltage, what happens? What will the output look like? It will saturate as soon as there's any difference. So as soon as I have any positive difference, the op-amp will saturate to the positive rail. If as soon as I have any negative difference, it will saturate to the negative rail, right? What happens if I have an offset voltage? From a circuit perspective, think of it this way. What would you need to do to create an output voltage that looks like this? You would need to add a source here, maybe of the minus the offset voltage. That way, minus the offset voltage plus the offset voltage, the sum here is 0, so that the input, the difference between these two now is 0 volts, right? So in this case, the input-output characteristics of the op-amp for an op-amp with a plus 5 millivolt offset, if you have a plus 5 millivolt offset, what does this mean? It means that the output will saturate as soon as what happens? What? So this is like what? So here the output was A times V2 minus V1. Here the output will be what? Without my source here, the output is what? Is V2 minus V1 plus V offset, because V offset is in the non-inverting. They put it in the non-inverting. So this is V2 minus V1 plus V offset is equal to V output divided by your gain, right? So if V2 minus V1 is 0, right? If it's 0, what is my output? The offset multiplied by the gain, right? So if V2, what? Yeah, it causes a shift, but so what do you want V2 minus V1 to be in order to get at the output of 0? I want to be able to know where this crosses 0. If I have a minus, V2 minus V1 is minus 5, and then this is plus 5, then the sum of this is 0, and hence the output voltage will be crossing 0 here. So this is the 0 crossing point for the amplifier with an offset voltage. Now, anytime the V2 minus V1 is different than 0, becomes minus 6 or minus 4. If it becomes minus 4, it will saturate to the positive rail. Right? If it becomes minus 4 plus 5 is equal to 1. So it's a positive 1 millivolt. So it means that V output will be, so 1 multiplied by an infinite gain is a positive infinite V output.
So
Yes,
is
sir.
that like a safety check to make sure that if V2 and V1 don't equal each other, it won't saturate? Or like what's the purpose?
No, this is something that would exist in the op-amp physically. Because of the circuit, remember this op-amp is not an ideal thing, right? The op-amp is made of transistors and resistors and capacitors inside it, right? This chip is made of devices inside.
Okay, why did they add the offset
They didn't
voltage?
add it. They didn't. It's a manufacturing process.
Yeah, but then why is it
Why?
zero?
This is chapter 12. Because when we get into, I mean, we discuss, okay, so in this chapter we deal with the op-amp as an application. So we design circuits using the op-amp block. In chapter 12, we deal with designing the op-amp itself. We're not going to take chapter 12, but we will study the chapter 4, the transistors and the MOSFET and BJT chapters. MOSFET and BJTs are the transistors that are used to design the op-amp. Right, so we have to study those first. If we study 326, if there's a 326 is another course. So if we take 326, we would cover that chapter 12 material. Right, but here we design, okay, we deal with this as an application from an application perspective. And then we dig a little bit deeper and see, okay, we will deal with these bias currents. We will see that when we design transistor circuits, oh, this is where this bias current is coming from. Right, so here I will just show, okay, there's bias current. There's offset voltage, right? The offset voltage stuff is dealt with in chapter 12 in a lot of detail. Yes, sir.
Now, after you said that, let's say it's minus 4 plus 5 equal to 1.
One.
Also, it's gonna be 0 at -5. Or
-5 plus 5 is 0, so that's where the zero crossing is. So if you're designing a comparator and your op-amp has an offset voltage, this is going to ruin your comparator. If you're comparing signals that are a few millivolts, right? If you're comparing a signal, let's say you're comparing two signals here, one signal here and another signal here, but here you also have the offset voltage. So these are the two signals you're comparing with respect to ground, with respect to ground. So signal 1 and signal 2, right? This is V offset. You have to consider it. It's a voltage that is at the terminals of the ideal amplifier. So now you're not actually comparing V1 and V2. You're actually comparing V2 plus V offset minus V1, which is this equation that we have here. Right? So it will, if you're running this as a comparator, it will affect your result.
So the offset just comes when it's built in.
It's something that is spec. It's a spec of the op-amp. You saw it in the data sheet, right? It exists. Its value is maximum. They don't tell you what exactly it is. They tell you it has a maximum value of so and so.
So they don't add it, it's just there. Because
No, it's just there because of the design of the op-amp. So it's the input offset voltage. When you design this device, you get this offset voltage. Also, when you design this device, you will get a large gain. When you design this device in a certain way, you will get a gain that is, large but not infinite. Infinite doesn't make sense. Also, when we design this device, we will get a gain that is, we said it's infinite bandwidth. Remember, that's one of the things we said about the op-amp, infinite bandwidth. If I put any signal with any frequency, it will respond with a gain, no problem. But this is not true either. We will see that it's a physical system, right? Any physical system will have some sort of limitation at the end. So we will see that the op-amp gain will also look like a low-pass filter. So it will have infinite gain for a certain period of time only, for a certain range of frequencies, right? And all of that is specified in the data sheet. So you may want to go and find another op-amp with a lower input offset voltage. So as a bonus, compare 3 op-amps on several, at least 5 characteristics, okay? Bonus, right? Bias current, offset voltage, gain bandwidth. We'll talk about gain bandwidth further. That's a bonus, half point. One or 2 pages maximum, okay? Not more. For next week, that's fine. Okay. Where's the textbook? Okay. So here. So we went through this example. So it's going to affect your comparator operation if you're operating as a comparator. How do you measure it? The way we measure it is the way I suggested. I suggested, okay, we cannot run it. We cannot just, okay, if you just put it as a comparator, fine. You will know that you have an offset voltage that is plus or minus, right? Because it's either going to be added to your V2 signal or subtracted from your V2 signal, right? If you run it as a comparator and you keep playing with your input signal until you make sure that the output becomes 0, then you know your offset voltage is so and so, 5 millivolts, right? So you can do it that way, but an easier way to do it was, okay, run it as an amplifier. Put it in the non-inverting amplifier configuration, but instead of having a source as your signal, remember we can use superposition with our amplifier circuits because they're linear. So one way to do it is, okay, build a non-inverting amplifier circuit around it, and don't put an input signal. Just take this signal at terminal 2 and ground it. Inside, of course, there's this offset voltage, right? Here they brought it outside to show you, but this is inside the op-amp, right? So this is inside your op-amp, right? So you just ground the non-inverting terminal. You know that the gain for the non-inverting amplifier is 1 plus R2 over R1. You will measure that gain multiplied by some offset voltage. So if you know that the input that you have placed is 0, then and you know your resistors, meaning you know your gain, you can calculate your offset voltage. You did not put anything external. So the only thing that's causing gain now is your resistors and the offset voltage. So you know what your offset voltage is from that perspective. So how do we deal with that? So fine, the designers of these op-amps designed them, and they found that fine, this is happening because of the design of the op-amp. So how do we deal with it? There's a offset nulling terminal typically in an operational amplifier. I don't know if the 741 has one or not. Let's check. Let's look at the terminals of the 741. Yeah, let's see here. So this is the package. See, offset nulling. Offset nulling. Right. So this offset nulling terminal is something that is used to deal with the problem we were talking about. So we know that there are two terminals, and we saw that there were two pins that were labeled offset nulling in the op-amp datasheet. And the way that was the op-amp was designed such that if you put some resistor, a potentiometer between these two offset nulling points, they create a voltage that is going to be used to offset the offset voltage, input offset voltage. It's inside the op-amp, right? How is this circuit? We don't know. This is not something we want to. We just want to. I mean, you just want to know that when you get a data sheet, you're a designer of the circuit. You're not designing of the op-amp now, right? If you're designing the op-amp, chapter 12, you need to deal with that. If you're designing the circuit, you need to deal. Okay, there's offset that I'm measuring. How do I deal with that? With an offset nulling circuit, I need to make sure that my op-amp that I'm buying has offset nulling terminals, and then I read the data sheet. How do you connect the potentiometer around this? What size of potentiometer? Blah blah blah, and then you can figure out how to get rid of your offset, yeah. But you cannot get rid of it, actually. You can get rid of it only in the certain condition that you're at today, right now. But what if the temperature changes? Right, the offset changes. Right, so it's something that you can minimize. You cannot get rid of. Right, so you can minimize, you cannot get rid of, yeah. One interesting way to deal with it, though, is what? This is a DC, right? So remember we talked about capacitor coupled amplifiers versus DC coupled amplifiers? So this is an interesting place where, fine, it would have been nice to be able to capacitively couple your amplifier. So one way to go around that is to put a input capacitor here. If I put an input capacitor here, right, what's going to happen to any DC components? Or what is the gain, actually? What is the gain? What is the gain of this circuit? What is the gain of this?
If you put a capacitor in DC, doesn't it just turn to an open?
What? A capacitor coupled inverting amplifier. Oh, excuse me?
If you put a DC,
If I put a capacitor in here, I don't allow any DC current to flow. Right? So that's, if I would like to make sure that I'm not, yeah. Let's calculate the gain. Let's look at the calculating the gain for this. This is a non-inverting amplifier, right? Equivalent circuit for determining its DC offset is V out. So let's make sure we calculate the gain for this. The gain for this, if this was a non-inverting amplifier, or actually let's look at the gain for this circuit. Okay, this is what? An inverting amplifier, right? It's R2 over Z1. This is the gain for this circuit, right? How about for DC? What did we do? For any DC circuit, for any DC component, if I'm going to put my signal here, that will be a DC signal, VI. What do we do? No, capacitor is open circuit. If the capacitor is an open circuit for DC, then this R doesn't exist. Right? So, okay, you have a sensor. This sensor is actually going to produce an AC signal, for example, that you want to pass through the amplifier, right? And that's this one. We're good? The gain for this inverting amplifier, we know, minus R2 over Z1. And we will have to include the frequency dependence of this Z1 since we have a capacitor. We agree with that? Sure? We're fine? Okay. Now, the op-amp also happens to have an offset voltage, right? This amplifier, if I have an offset voltage, it will exist here, like, right? It will, as if, let me delete this. It will also exist here. This is my V offset. Do we agree? This offset voltage, I would like to see what is the effect of this offset voltage on the output. Correct? So we saw that for the non-inverting, the offset voltage was being amplified. Correct? How about for the inverting amplifier?
So if we didn't add the DC voltage,
Here?
we didn't know that VI.
VI? This is your sensor. Your sensor wants to pass AC through, actually. Okay, it wants to pass AC through. It's a AC signal. You want to pass some time varying signal through. You want that to go through, right? So, what is the capacitor going to do if this signal is DC? It will be an open circuit. What if the sensor is? What if this signal is an AC signal? It will allow it to go through with a certain impedance, right? So it's going to allow my signal to go through, my physical signal of interest to go through with a certain impedance. That's fine, okay?
So you said the capacitor eliminates the R1.
No,
through
I
this-
didn't say it eliminates the R1.
Oh,
No, I said R2 over Z1 is the gain of this, of the what? Of VI, V output to VI. V output 1. Remember here I have two sources.
okay.
Because of the offset, I have two sources that are going to affect my output. Superposition will apply to op-amp circuit. So I can look at, if I know this is going to happen, then I can look at it two ways. I can draw the op-amp ideal without my offset. And then I can draw the offset only. And I look at the output in this case, V output 1, this is V output 2. And my actual V output is V output 1 plus V output 2 from superposition, right? From superposition, I want to build an inverting amplifier. The inverting amplifier gain is R2 over Z2 over Z1, okay? This is my inverting amplifier gain. My signal here that has some AC content that I would like to see is going to be amplified by R2 over Z1 with a negative sign. That's going to be V output 1. And I did not include offset voltage here. I just made this connected to ground. But this offset voltage exists. So how do I see what the effect is on the output? I add it to here. I include it here on the same circuit. But now what's happening to the circuit? This circuit now is, what do you do to a voltage source in superposition? In superposition, you short the voltage source and you open circuit the current source. Right? So you short the voltage source. Right? I would short this voltage source. And I don't have a current source. So I shorted this source. And now I've added what? I added my offset voltage. I added my offset voltage here. So I don't have a ground anymore. This is V offset, which is what I have here. But I'm just going to show how this circuit became this. So I added my offset voltage here. When I add this, so I add this offset voltage, I made this ground. What is the voltage here? Because we have feedback? No. Offset. Right? This offset voltage is a DC value. This DC value can push current through here if there was no capacitor. But because I added the capacitor is open circuit for DC. So that's why the circuit became this.
Okay, so because of the offset, C is a short circuit.
No, C is
Oh,
an
C
open
is an
circuit. Exactly. So C is an open circuit. So now, what's the nice thing about this circuit? I did not. So now this is my new circuit. My new circuit. What is the gain? This is a what? This is a non-inverting amplifier. Gain is 1 plus R2 over R1. R1 is infinite. So this goes away. So what's happening to my output due to the offset? I'm not amplifying the offset. Remember before in the non-inverting circuit, this is an inverting amplifier. In the non-inverting amplifier circuit that I had here, what was happening to the offset voltage? It was amplified. That's not a good thing because it eats up from my margin of signal, right? The signal wants to be between my supply rails, plus minus 13 volts, for example. Here I'm amplifying the offset voltage. That's not good. So, building a non-inverting amplifier when you know that you have offsets may not be interesting. So that's why you would go and build a non-inverting amplifier in this case. You may end up doing that, right? So we found that the non-inverting amplifier deals nicely with the offset voltage problem because I can pass my signal through and amplify my signal through with whatever gain that I would like to control, right? And I have to live with having some offset voltage, even though I trimmed it and nullified it and blah blah blah. But I'm not at least magnifying it, right? So that's the benefit of this capacitively coupled amplifier. Remember the first chapter we talked about this capacitively coupled amplifiers and how they dealt with the frequency response of my by my circuit, right? So they made the gain, versus frequency look like something like this. They had attenuation here and attenuation at high frequency. And we said that this is due to the fact that they're called capacitively coupled amplifiers. So that's the benefit of having capacitively coupled amplifiers. The op-amp inherently is DC coupled, meaning it has a characteristic like this. So it does not attenuate at DC. That's why you would add this externally if you want to deal with the offset voltage. If you have a problem with the offset voltage, okay? Too much time. But everybody's good with the offset voltage issue? Okay, so now what's the next non-ideal issue? Bias currents. So bias currents are currents that are actually, so we've always said, we assume currents flowing inside here to be zero at the terminals of the op-amp. So this is not the case. So because you have transistor circuits inside, and we will see from as soon as we finish the diodes chapter that transistors require some bias current to operate. This is not, they didn't even start to operate, they're just getting ready. Okay, they're ready and then they start to operate. So just for them to be ready, they require some bias currents. Okay, so this is due to that. It's not due to the fact that your input impedance is low or high or whatever. This is due to the fact that you have transistors inside this block. Okay, so bias currents. So we want to define two things. So fine, they're called input bias currents. That's one, and they have an average value. So sometimes you don't want, they're different. In the general case, the bias current at input terminal 1 and the bias current at input terminal 2. In the general case, they're different. They should be reasonably close to each other. So sometimes we deal with the average value of them. So we call that the input bias current. We call that the input bias current, and we will deal with that sometimes. So we simplify the equations here. And then another interesting definition is the input offset current. So the difference between the bias currents is called the offset currents. Why is this important? Because we will see that when we deal with the bias currents, we'll be sending their effect will be only due to the offset. If we don't deal with them, their effect will be due to the value of the bias current, right? So remember, the value of the offset current is the difference between the bias currents. If they are very similar, then what is the offset current? Much smaller than both of them, right? So if I'm able to come up with a circuit that does not, is not affected by the bias current itself, but affected by the offset current, then it's nice. It's better than, it's like not magnifying the offset voltage and dealing with and sending through only the offset voltage through, right? Like we had before. So it's same sort of mentality, same sort of issue. So what is the effect of the bias current? So let's look at this circuit. So in this circuit here, I have my bias currents are IB1 and IB2, right? I would like to see what the effect is on my output. Remember, my output voltage is equal to what? Again, this is current IB1 flowing through here. This is IB2 flowing through here. This is IB1 flowing through. I have feedback. As soon as I have feedback, I know that the voltage difference between these two nodes is 0. This node is at 0, then this node is at 0 as well. If this node is at 0, then there's no current flowing through here, right? If there's no current flowing through here, then where is IB1 gonna come from? Through this resistor, right? IB1 is existing. I mean, we have to agree. IB1 will exist. There's no current through here, so IB1 will go through this R2. So it will cause a voltage drop equal to what? Equal to IB1 times R2. So IB1 times R2. So V output minus IB1 times R2. IB1 times R2 is equal to 0. So V output is equal to IB1 times R2. And that's what we have here, right? So what is the bias current doing to the output? It is amplified by my resistor R2, and I'm multiplying it by the actual bias current. And assuming the two bias currents are equal, I can substitute IB1 here or IB2 or just IB, right? We said IB is the average value of both of them. So is this good or bad? It's not nice, because if I'm building a inverting or non-inverting amplifier, what was the gain of the inverting amplifier? In general, it was minus R2 over R1. So here, If I want a large gain for the inverting amplifier, what do I need to make R2 large, right? If I make R2 large, what happens to the effect of the bias current on the output voltage? It increases. So they're conflicting again. So I want to make my amplifier gain large by making R2 large. If it's an inverting amplifier or a non-inverting amplifier, same, right? Because the other was 1 plus R2 over R1. So, but I face a problem that if I make R2 large, I'm actually magnifying the effect of the bias current that has on my output, which is a problem. So how do we deal with that? We have to add another component to the circuit. That's what we've been doing. We have a problem, we deal with it with another component in the circuit. Yeah. So let's look at this circuit. Okay. We just added a resistor here. Okay. So if we do that, how does this help? So again, I have feedback, right? That makes the difference between these two 0. We agree to that. However, in this case, when I add a resistor and I have this current flowing here, there is a voltage here. It's not 0. So this voltage here is what will also appear at this node. What is this voltage? This voltage is this current IB2 multiplied by R3, but with a negative sign, because if it's a positive voltage, the current should go in the opposite direction, right? So if it's a positive voltage, the current should go in the opposite direction. So that's why it's written as a negative IB2 times R3. Okay, so that means that I have also negative IB2 times R3 here. So this is the voltage. This voltage divided by, so it's IB2 divided by R3 divided by the resistor R1 will produce a current, right? That is equal to the voltage divided by R1. So IB2 R3 over R1. So that's the current flowing through here. What happens to this current and this current and this current? You apply Kirchhoff current law at this node. So the current coming in is IB2 R3 over R1. Or actually, you want to calculate this one. This is what we want to calculate. So this is Ix that we want to calculate. So IB2 R3 divided by R1 is coming in. Ix is coming in. And the output is IB1. So you can calculate Ix is equal to IB1 minus IB2 R3 over R1. IB1. Before, what was it? What was the current flowing here without this resistor? It was IB1 before. Now I reduced it. I reduced it. And I made the reduction dependent on the value of R3 and R1. Is that good or bad? Probably better if I reduce the value of current going through here, because this current is, again, this voltage here. The output in this case will be what? The output is this voltage here is equal to, this current is flowing this direction, so it's equal to this, and then this voltage exists. There's a voltage here between ground and this node, so you have to consider that as well. And this is equal to minus IB2 times R3. So the output voltage is equal to, you take Kirchhoff voltage law around this loop. This loop will contain this voltage, and this voltage. So let's look at the equations. So here, the output is equal to minus IB2 times R3, which is the voltage at this node, right? Plus IB plus R2, which is this resistor here, times this, all this current, right? So the output voltage this one here is equal to this voltage drop plus this voltage drop. So this voltage drop here is this one, and this voltage drop here is the voltage across this resistor R3, due to the fact that you have some bias currents. We said that these two are close to each other, so sometimes we can say, okay, let's assume that it's IB2 is equal to IB1 is equal to IB, so then we can simplify the equation a little bit and write the output as this, okay? So this is, what is this telling us? This is giving us the effect of the bias current on the output voltage. Right? This is giving us the effect of the bias current on the output voltage. How can I get rid of it? By looking at this equation, come on. Or how can I minimize it?
You want the output to be zero?
Yeah, I would like the output to be 0.
Have to,
IB equals
How can I make the output equal to 0 in this case?
have to,
If I make all of this equal to R2, right? I get rid of the output voltage component due to the bias current, right?
So that means R1 has to be pretty big.
Or I can just design R3 properly. So because you want to keep R1 and R2 to be independent, because you want to be able to control the gain of your amplifier, right? So the one nice way to go around it would to make R3 equal to R2 over 1 plus R2 over R1, right? That will cancel this effect completely, right? These two will cancel and they'll be left with R2 only. So then R2 minus R2 is 0 and then the output component is gone, right? So that's one way to go around it. What did this bias? I mean, what is there a drawback here? Of course. I mean, you're adding another resistor. The perfect matching between resistors is an issue, but you're going to be able to reduce that component significantly. Okay, so that's what they say. That's what we're talking about here. If you do that, actually, if you do that, we'll cancel it completely, which is not going to be exactly possible because of the matching issue. How about if you go back to this equation and you substitute with, remember, IB, the input bias current, was the average value of, if we go back to our definition for input bias current, I had their average value, IB was equal to IB1 plus IB2 over 2, right? We said that they're very close to each other, but they're not exactly equal yet. So one way I can rewrite IB1 as IB plus I offset over 2, where I offset is equal to IB1 minus IB2, right? That was the definition of I offset. I offset was the difference between these two. If you solve for IB1 and write IB2 in terms of I offset and IB1, right, then you can write an equation for IB1 in terms of I offset, right? So from this equation and from this equation, you can write that IB1 and IB2 are equal to IB plus I offset divided by 2. You can solve for them this way. If I do that and I substitute in this equation, what do I get? It's not going to be obvious when you look at it, but we're not going to derive it. But if you do that and substitute in this equation, in 2.38, what you get is the following. So if you do that and you substitute in equation 238, what you get is that the V output will be equal to the I offset times R2, right? So what's the advantage of this? It's much smaller. No, it's not to see the effect. The effect is there. The effect is there, and you saw it in the output voltage. You saw it in the output voltage without adding R3. When we added R3, we had to select a value. What is the good value for R3? We selected the value for R3 to try to make the output as much as possible 0. But that's assuming that the bias currents were the same, exactly the same. And that's assuming that playing with this equation. After we did that, okay, we still measure some output due to the bias current. So how do we deal with it? So what is this output equal to? The output is equal to, exactly, so if you go back and substitute with actual values here in terms of bias current. So IB1 in terms of the average value of the bias currents. IB2 in terms of the average value of the bias currents. you'll find that the output voltage is the difference between so the input offset current times R2. This is much smaller than what we had here. This is what? This is the input, this is the bias current times R, initially it was the bias current times R2. So offset is the difference between the bias currents. So now I have the two subtracted from each other. So it's a much smaller quantity. So V output due to the bias current will be much smaller if you put R3 and select R3 such that you try to eliminate this, but you will still be left with some component because of the mismatching. So what is this component equal to? This component is equal to the offset current multiplied by the resistance R2. Okay? So,
Chapter 2 so long.
huh?
Chapter 2 so long.
Yeah, the chapter is so long, but we're almost done. Yeah. If again, there's a special case that I'm not gonna spend too much time on. If there is input capacitor coupling, so our circuit here was connected to ground, but if I have input capacitor coupling, what's gonna happen? Remember when I derived here, what did I do? I assumed that this voltage is equal to this voltage. If I have a voltage here, current will flow. But what if I put a capacitor here? Is current going to flow? Current will not flow. So if current does not flow, then the current here is 0. It goes back to the very similar to the previous case. If current becomes 0, there's no current flowing here, then there's no voltage. There's no voltage due to this current, right? So because I have a capacitor, if I put a capacitor here, if I capacitively couple this amplifier, there's no current flowing in here, right? But what's going to happen to if I have feedback, what's going to happen to the voltage at this node? Equal to the voltage at this node, right? Just because I have feedback. And then, since I have no current here, then I don't care about what's happening to this device. Remember the Kirchhoff current law at this node? I don't care anymore about this because the current flowing through here is now IB1, right? But what is the output voltage? The output voltage is still this voltage plus this voltage drop plus this voltage because that's the voltage here, right? So in the previous case where I did not have this resistor, this voltage was 0, right? So the output voltage was equal to the voltage across this resistor alone. Now, when I capacitively couple here, it's like opening this circuit completely, right? It doesn't exist, right? But here, I added my resistor R3. I added the resistor R3, so current will flow. This current is flowing. IB2 will flow, meaning there's a voltage at this node. And since I have feedback, then the voltage at this node and the voltage at this node are equal to each other. This is not 0 volts anymore. So the output voltage now is not IB2 times R2, right? It's IB2 times R2, so it's this voltage drop across this resistor, plus this voltage due to the presence of R3, right? So now, how do I select R3 in this case? Before I selected R3 so that I can eliminate the effect of whatever was in parentheses in R2. How do I select R3 now? I want to select R3 such that the voltage drop, so the voltage drop across this, the current flowing this way, so there's a voltage drop this way. The current is flowing this way, so there's a voltage drop across in the opposite direction. These two voltages are opposite of each other. If I make this voltage, V1, equal to voltage V2, then if I go around this loop, I see the voltage output is equal to minus V2 plus V1. The output is equal to minus V2 plus V1. If I make them equal to each other by proper selection of R3, right, which is what? In this case, if I assume that IB1 is approximately equal to IB2, then I want what? I want R3 to be equal to R2. Because if the current flowing through here is equal to the current flowing through here, and I make the resistors equal, right? But just the polarity of the current flow makes the voltages in opposite directions. That means I want the resistors to be equal to be able to cancel the effect of the bias current in the output. Right? So that's effective bias current even in the special case that I did not care to cover. Okay, we didn't finish chapter 2. I mean tomorrow for sure, inshallah. But yeah, we have to. I mean I cannot continue tomorrow.
That cancel chapter 5.
Chapter 5? No way. No. But the stuff we will cover tomorrow in chapter 2, I will go through quickly. I mean, it's we don't go. It's here. This talks about effect. We talked about the effect of finite gain, right? A, not infinite gain. What this section talks about? Okay, this A gain is not just finite. It's also frequency dependent. So it looks like a low pass filter, right? So what is the effect of that? We take our low pass filter equation, which we know. This is the format for the low-pass filter equation, and plug it into the derivation that you derived for the non-inverting, or for the derivation that I derived for the gain with finite A for the inverting. Okay? And the result will be what? Will be something that looks like, I'll show you the result. The result is, so this is the gain that we derived for the inverting amplifier with finite gain. I take this A, and from the previous section, it's the A that depends on frequency now, and plug it in. The A that depends on frequency is here. I plug it in, I simplify, I find the new gain. The new gain happens to look like what as well? For the inverting amplifier? Like a low-pass filter. I do the same for the non-inverting. Also becomes a low-pass filter. Right? And they both have the same break frequency. This is the break frequency. The break frequency is omega t over 1 plus R1, R2 over R1. Omega t, 1 plus R2 over R1. It's the same break frequency. So they will both, the inverting and non-inverting amplifiers are both going to become like a low-pass filter. Makes sense. I mean, again, they're physical systems. You're passing a signal through them. You want to integrate it, or you want to flip it with a gain, or just apply a gain. Is this gain going to be for infinite bandwidth? I mean, it puts frequencies with infinite bandwidth? No, they will be frequency dependent. We saw that they were frequency dependent by, in chapter 1, the last problem where you had a capacitor. We saw that there was some frequency dependence there, right? And this is where it is. This is the capacitors in chapter 1 stuff. And we did not relate it back then, but this is the effect of this capacitor in chapter 1. So basically I finished. We'll spend a little bit of time on this tomorrow, but yeah, tomorrow is for sure the last. But still, I mean.